All right, thank you very much. It's really a pretty amazing group here. So thank you for inviting me. I'm going to talk a little bit about an algebro-geometric theorem, despite this being a topology conference. And the idea is that after introducing a few things and stating the theorem, which I don't necessarily expect all algebraic topologists to, you don't have to necessarily know what all the objects are to follow what I'm saying. Then I'm going to go into a topological proof of the theorem. So as soon as possible, I hope to transition into some algebraic topology. But I want to start with a situation where we have a QCQS p-adic formal scheme. And let's say that is P quasi-syntomic, which is some niceness condition, something like smoothness or LCI, but just a nice p-adic formal scheme. And then in this situation, work of Bargov-Bott, Jacob-Lurie, and Drinfeld gives you a way of computing certain cohomological invariants. So what they do is they associate to this scheme certain stacks. So stacks presented in a way that's hopefully familiar to homotopy theorists. So there's going to be two of these stacks that I'll be particularly interested in. So there's the prismatization, which is some stack depending on x called x prism. And it's going to be a stack living over the moduli of formal groups. And there's going to be another stack, which is the syntomification. And that is also living over the moduli of formal groups. So in homotopy theory, we are hopefully very familiar with this moduli of formal groups because one studies the Adams-Novikov spectral sequence. And that's a spectral sequence whose E2 page is the cohomology, coherent cohomology over MFG of certain line bundles, these powers of the cotangent bundle, and that converges to the pi 2j minus ith homotopy groups of stable sphere. And so the cohomology of certain line bundles over MFG give you the algebraic starting point for perhaps the most theoretically important spectral sequence that computes the homotopy groups of spheres. So this, just to repeat what I said, the Adams-Novikov spectral sequence starts with coherent cohomology over MFG of these line bundles. So similarly, one can define, and this is perhaps my preferred definition, of the prismatic cohomology of X. And this will be bigraded if I say that we're also going to account for the so-called Brühl-Kissen twists. And so one defines this as the cohomology of the pullback of the same line bundle to X prism. So I don't think you need to know what X prism is to understand the formalism of prismatic cohomology, the way this is set up, and why it might start to be related to something in homotopy theory. We're just taking some construction based on X of some stack mapping to MFG, pulling back the bundles that give us the Adams-Novikov E2 page, and trying to calculate the cohomology over whatever X prism is. Okay, so say similarly, the syntomic cohomology of X with these various Broca's and twists is defined using X syn, again, just by pulling back these bundles, these line bundles over MFG and taking coherent cohomology. All right, so understanding things in this way makes it clear that that you can make the following construction. So let's fix integers a and b such that mu star mod p to the a, v1 to the b is a well-defined mu star mu comodule. So if you like, you can think of this as some sheaf on the moduli stack of formal groups. And then having fixed such a thing, I can define the mod p to the a, v1 to the b syntomic cohomology of X via this stack where I just take, let's say I take MFG, I look inside of it at the closed object where I set p to the a and v1 to the b to 0. Here I have my X syn, and then I just take a pullback. I write here X syn p to the a equals v1 to the b equals 0. So then I can continue to just pull these omega tensor j back to here, and that's going to define syntomic cohomology, now not with coefficients in ZP, but with coefficients mod p to the a, v1 to the b. And this turns out to be a thing that is useful and that algebraic geometers have discovered, maybe without thinking about homotopy theory. And I'll just remark that from this point of view, it's not entirely clear why I'm only saying I want to mod out by a power of p and a power of v1. You might want to mod out by, say, a power of v2 or something like that. But in fact, X prism and X syn are fundamentally height 1 objects. They're fundamentally concentrated at heights at most 1. And one way of making sense of that is just to say that, in particular, V2 acts trivially on mod p of v1 syntomic cohomology. So I can talk about some action of v2 just because this lives over MFG, but it will be a trivial action, and so it's not very interesting to take coefficients mod anything other than a power of p and a power of v1. So then I want to talk about a theorem which is joint between myself, Ishan Levy, and Andrew Senger, which, let's say, fix an integer n greater than or equal to 0, then there's two facts. One is that the functor x mapping to x prism p equals v1 to the p to the n equals 0 factors through the functor x maps to x p to the n plus 1 equals 0. And the other statement is that something similar happens with syntomic cohomology, where if I want to study mod p v1 to the p to the n syntomic cohomology, that factors through x mapping to xp to the n plus 2 equals 0. So what this says is that if you want to calculate prismatic cohomology, and you're willing to work mod a power of v1, you don't actually need to know your original object as a p-adic formal scheme. You only need to know what it looks like mod p to the n plus 1. And syntomic cohomology, similarly, if I work mod v1 to the p to the n, is in fact determined by some p power reduction of the original object. It's a slightly more, slightly different p power reduction. Here I have to mod out by p to the n plus 2 instead of p to the n plus 1 for prismatic cohomology. So this statement is hopefully supposed to be reminiscent of a feature of deRham and crystalline cohomology, which is this classical fact that if I take p-complete deRham cohomology, that depends only on the crystalline cohomology of the mod p reduction. And so that's why I'd like to think of these as some kind of crystallinity statement. It says that, that you can learn something about prismatic or syntomic cohomology only from these mod p reductions. Maybe just another comment is that this is some kind of very quantitative version of redshift, which should be a general feature, that somehow the p-adic filtration on X itself has become the v1-adic filtration on its prismatization or its syntomification. All right. So I want to kind of explain why you might be able to prove such a thing or why you might believe such a thing. And I'll point out at the outset that these are objects in pure algebra. So in principle, you should be able to just write down in algebraic factorization of that functor. And I am partially speaking here in hopes of maybe learning if one of you would view this as obvious, or I think it's somehow okay from a functor of points perspective to prove the prismatization one, but it was somewhat tricky from a functor of points perspective, at least for us, to prove the syntomification one. Though at the end of the day, one can give a functor of points proof of this. So there is some kind of algebraic proof of this, but maybe I'd like to talk about sort of why topology suggests such a statement and maybe can be used to prove such a statement. So for simplicity, let's assume that X is affine, so it's spoof of some ring. Remember, it's some p-adic formal scheme, so I'm putting a spoof. Note the p-adic filtration on this ring. And R should be a somewhat nice ring, so R is P quasi-syntomic. Some condition like being LCI or smooth. Okay, then here's a kind of key fact. This gadget you assign to X, namely X prism living over MFG, or this other algebraic thing you can assign to X, namely X syn living over MFG. They are both functors of THH of R considered as in E infinity THH of Z algebra in cyclotomic spectra. So in a moment, I'm going to remind you a little bit about cyclotomic spectra and what THH means. But THH of R is some cyclotomic spectrum. I'll say what that is in a moment. And the point is that just from knowing this, with a little bit of extra data, this is structure of its algebra structure over THH of Z, you can recover these constructions. And I really mean these constructions, for those who might be wondering, I'm not talking about any Nygaard completions or anything like that. So I like to think of THH of the ring as some kind of master p-adic cohomology theory, at least for these kinds of p-adic cohomology theories. It knows about syntomic cohomology. It knows about prismatic cohomology. It also knows about other things like TC, which is more directly related to algebraic K theory. So if we can prove something about THH, it will be, in some sense, strictly better than proving it about syntomic cohomology and prismatic cohomology. So let me just give a brief review about topological Hochschild homology, namely THH. And cyclotomic spectra. Okay, and from now on, let's implicitly P complete. So I'm always going to be thinking about P-completed spectra and things like that before I make a mistake by forgetting that. Okay, so let's just recall the definition of a cyclotomic spectrum. Definition, a cyclotomic spectrum X is a spectrum with circle action and a map, an S1 equivariant map, from X to X to CP, where here we're putting the prescribed circle action on X, and here X Tate CP inherits an S1 mod CP action, but that group is isomorphic to S1, and under that identification, we're demanding this map be S1 equivariant. And so just a remark is that the category of cyclotomic spectra, as set up by Nicholas and Schulze in this way, is symmetric monoidal. And another interesting piece of structure is that there's a T structure on that category as well. So there is a T structure on this category. And that T structure was defined and studied by Antio and Nicholas. So in fact, it's pretty easy to characterize connectivity in this T structure. So a cyclotomic spectrum X is connective in the Antio-Nicholas T structure. exactly if and only if the underlying spectrum. So forgetting about this Frobenius map and forgetting about the circle action, the underlying spectrum is connected. So it's not too hard to see whether or not things are connective, but it turns out that being bounded above is a bit more of a mysterious property, as we'll see in a moment. So the basic example is that if A is an E1 ring spectrum, then I can take THH of A, A tensor A op over the sphere. This turns out to be a cyclotomic spectrum. So it admits a circle action, it admits an S1 equivariant Frobenius map, and furthermore, if A is connective, so is THH of A. So if A is not just an E1 ring, but if A is an E infinity Z algebra, for example, if A is a discrete classical ring, then THH of A is an A infinity THH of Z algebra. And so again, what I was trying to indicate previously is that if A is a discrete P quasi-syntomic ring, then this structure of THH of A as in E infinity THH of Z algebra is sufficient to recover things like the prismatization and the syntomification. But it also knows more. This also knows about TC of A. So definition, TC of A is Hahns in this category of cyclotomic spectra from the unit of the symmetric monoidal structure into THH of A. And that's an invariant that is not quite the same as prismatization or syntomification or anything like that, but is more closely related by the Dundas-Goodwillie-McCarthy theorem to algebraic K theory. In particular, for many of these p-adic rings in particular, especially thanks to work of Akil and Dustin, calculating TC is more or less the same problem as calculating algebraic K theory P completed. So then there's a theorem of Antio Nicolas relying on work of Boxton, which is that THH of FP is bounded in the cyclotomic T structure. So THH of FP as a spectrum turns out to not be bounded above, but nonetheless, THH of FP as a cyclotomic spectrum is bounded above in this cyclotomic T structure. And I want to pay close attention to what things are bounded above. I don't know, just because I like to, and because it was used, for example, in the disproof of the telescope conjecture and things like that. Okay, so another example. That any spectrum can be given the trivial cyclotomic structure which means just take that spectrum, view it as having a trivial S1 action, and view the Frobenius map as some kind of canonical map from something with trivial action to its Tate. And then there's a nice theorem. I guess I'll attribute this to Nicholas, but the main computation that goes into it is due to Hesselholt and Madsen, I believe, which is that if I take THH of Z and I tensor it with the trivial cyclotomic spectrum on S mod P to the A V1 to the B, and this is for any A and B such that S mod P to the A V1 to the B exists. So if I take that tensor product, again remembering that cyclotomic spectra form a symmetric monoidal category, this is bounded in the anti-Nicholas cyclotomic T structure. Okay, so this is a fairly non-trivial result. For example, this implies the so-called Quillen-Lichtenbaum conjecture for the algebraic K-theory of QP, but it's actually maybe a little bit stronger than that. And it was originally proved by Hesselholt-Madsen in service of proving this kind of Lichtenbaum-Quillen result. Okay. So then I want to say a theorem. This may be work in progress or something we're currently writing down. Myself, Ishan, and Andy Senger. Suppose R is an E infinity Z algebra. In other words, something like a classical ring. And let's suppose that we've chosen A and B so that S mod P to the A, V1 to the B exists. Then for sufficiently large integers n, if I take the THH of R and I mod out by P to the A and V1 to the B, this can be functorially recovered from the THH of R mod P to the N. So this is not just a spectrum statement, but a statement as cyclotomic spectra. And in fact, by Berkland's work, this sometimes admits a ring structure. And when it does, as long as you choose n large enough, this theorem will recover this object as a ring in cyclotomic spectra. And so the claim is that this really depends functorially only on this. So this implies all of these crystallinity results in algebra about syntomic cohomology and prismatic cohomology. But it also implies some kind of crystallinity result for TC, for example.
Jeremy, when you say functorially recovered, like, what structure do you need on THH?
Yeah, sorry. Maybe I shouldn't even be saying this. I should say from R mod p to the n as a z mod p to the n algebra. Is that okay? Maybe if I wanted this as an En ring, I need to know this is something like an En plus 1 z mod p to the n algebra or something like that. So what is the idea? So for simplicity, let's assume that maybe following Berkland, we can think of this as a ring, maybe an E2 ring even. That should be way more than enough structure, but it will make the argument clearer. So we will produce a diagram THH of z. Well, that maps to THH of z mod p to the a v1 to the b, but it also maps to THH of z mod p to the n, which maps to THH of z mod p to the n, mod p to the a, v1 to the b. And then the mysterious thing we're going to do is produce an arrow like this. So we will produce, for n large enough, a map of E2 rings in cyclotomic spectra. Okay, I will explain to you in a moment why you might believe such a dashed arrow exists, but let me say why the existence of such a dashed arrow implies some kind of crystallinity statement like this. Sorry, this n here? Yeah, so the idea is that you want to recover this for fixed a and b, and it will depend on the mod p to the n reduction of r for some very large n. And I was explicit earlier about which n in some cases in algebra, but here I'm just going to try to sketch that as long as n is large enough, you'll be able to do this. Okay, so before producing that diagram, let me say what it has to do with this result. So assuming the diagram, I can look at THH of r, and I can tensor it over THH of z with THH of z mod p to the a v1 to the b. And that, of course, will just be THH of r mod p to the a v1 to the b. But on the other hand, because of this factorization, I could think of this as THH of r tensored over THH of z with THH of z mod p to the n tensored over THH of z mod p to the n with THH of z mod p to the a v1 to the b. In other words, tensoring down along this map factors through tensoring down along all these intermediate maps. But now this expression is the same thing by symmetric monodality of THH, and these are all E infinity ring maps, as THH of R tensor Z, Z mod p to the n, tensor over THH of Z mod p to the n with THH of Z mod p to the a v1 to the b. Right, so we have now expressly written this as something that obviously depends only on R mod p to the n as a Z mod p to the n algebra. So then, of course, all the content in the theorem is about producing this dashed arrow, at least when n is sufficiently large. But I hope you can see that we're arriving at some kind of concrete problem. We're no longer proving something about every ring. We're just trying to produce a specific E2 ring map. So why should it be feasible to produce such a ring map? Well, by this Lichtenbaum-Quillen conjecture, this result of Hesselholt-Madsen, if I take THH of z and I mod out by p to the a and v1 to the b, that's just equal to some truncation in this Antio-Nicolas T structure of the same thing. Right, so it is bounded, so it's equal to its own truncation, and it's also, bounded below because it's connective. So therefore, it suffices to produce the dashed arrow out of not THH of z mod p to the n mod p to the a v1 to the b, but its truncation in this mysterious T structure. Because we're trying to map into something truncated, we can just map out of the truncation. And now, right. So we kind of reduce to the following more basic theorem, which is that for any given integer, 0 less than or equal to I less than or equal to this truncation bound n, if I look at the ith cyclotomic homotopy group of THH of z mod p to the n mod p to the a v1 to the b, This is pro constant as n varies. And it's pro constant exactly with values the ith cyclotomic homotopy group of the THH of Z mod p to the A, V1 to the B. So we're trying to show that this tower of truncated things is pro constant, and because it's truncated, it really just suffices to check it on each homotopy group individually. And so now this turns out to be closely related, though I think not exactly the same, as continuity statements. So this is some kind of thing saying that on each cyclotomic homotopy group, this is continuous. So this is closely related to continuity statements appearing in work of Dundas Morrow. There's some statements along these lines in papers of Clausen and Matthew, and also in Antiu, Matthew, Morrow, Nicholas, this Bailenson fiber square paper. But so at the end of the day, you have to make some kind of computation, and I actually claim that you can just brute force this, which is something I'll talk about in a moment. So using, for example, this BMS Spotmore-Schulze-Motivic filtration, you can just literally compute these. They're all going to be in an abelian category, and you can just observe their pro constant. So that's, in particular, if you already believe in these crystallinity results in pure algebra for syntomic cohomology or prismatic cohomology, it's very easy to use the BMS filtration to prove this is pro constant, because in every given homotopy group, the BMS filtration is a finite filtration. All right. So how much time do I have left?
15 minutes.
OK. So in 15 minutes, I want to give some applications of crystallinity. But are there any questions before I jump into the applications? So, and I haven't really explained how to do that calculation, but I claim it can be done. Yeah.
When that prime p, is that odd, or does this work at p equals 2 also?
It should work at p equals 2 whenever this exists.
Whenever it exists, gotcha.
Yeah. So maybe a first application. TC of Z mod p to the n. OK, I want to start to think about these groups, and right after Dan Isaacson asked me this question, I'm going to suppose, for simplicity, assume p is odd. So what is the status of knowledge of these groups? So for a long time, they weren't very well understood at all, though there was partial progress by people like Engelweit. Right, so there's this recent work of Antiu, Krause, and Nicholas. And what they do is prove both some theoretical results about this object and some computational results. So they give an algorithm to compute this for any star. And the situation is a bit like the homotopy groups of spheres. Like if you look at Z mod 4, maybe they can compute the first 100 before a supercomputer starts having trouble. If you look at Z mod p to the 7th or something, they compute maybe the first 10 or 20 before the supercomputer runs into trouble. But they do have an algorithm to do it. And by runs into trouble, I just mean runs out of memory or something like this. But also beyond giving an algorithm, just by thinking about their algorithm, they proved some interesting theoretical results, some very interesting theoretical results. So they prove that when star is both large and even, this is trivial. So the bottom few even homotopy groups of this are not trivial, but eventually they all become trivial. And finally, they in this range, so when star greater than 0 is odd, the order of this group is p to the I minus 1, sorry, the order of tc 2i minus 1, or z, maybe I should say of k, which is closely related to tc. Z mod p to the n is p to the I minus 1, p to the I times n minus 1. So, okay, in other words, thanks to their work, we have an algorithm to compute this, at least for small values of star and n. We know that for large values of star, this is trivial in even degrees, and in odd degrees, they explicitly understand the order of the group, but they don't understand what the group is. So there's still a question of, for example, how many direct summands appear in the standard representation of this finite cyclic group. Okay, so then what does crystallinity have to do with this? So here's a quick theorem. There's an iso of graded FP vector spaces pi star of Tc z mod p to the n mod p v1 to the k. That's going to be the same as pi star Tc of z mod 0 mod p v1 to the k, so long as k is less than or equal to p to the n minus 2. All right, so crystallinity says that as long as I'm willing to work mod a power of v1, then I can reduce this mod a power of p. But mod a power of p, p to the n might as well be 0. So by z mod 0, I mean something like an exterior algebra on a degree 1 generator. So I'm taking the derived quotient by 0. So this is just the trivial square 0 extension of z by the suspension of z. And so this thing, because it is a trivial square 0 extension, can just be computed using some formulas for Tc of square 0 extensions that were developed by Lindenstrass and McCarthy when they were studying how to prove the Dundas-Goodwillie-McCarthy theorem. So this can be, so we can completely and explicitly compute this. We can just write down a vector space basis for this. And so that sort of gives, in contrast to these results, a complete computation, a closed form. But instead of getting integral groups, we're getting groups mod p v1 to the k. But maybe I'll just point out that knowing the groups mod p v1 to the k for k smaller than or equal to p to the n minus 2 tells you some things about the integral homotopy groups.
Sorry, I'm a little bit confused here.
Yeah.
So when you say what existing isomorphism, do you mean like it's induced by a natural map from Z to 0?
No, it's not induced by any kind of map. It's just the statement that that functor is dependent only on the
Okay. I see.
reduction of the ring, and those two rings have the same reduction mod suitable powers of P. Right, so maybe I'll advertise now a theorem of Joachim Krause and Andy Senger. So by combining this knowledge that they have here in their algorithm with the explicit names of generators we come up here, we learn that Tc to I of z mod p to the n is non-zero if and only if p minus 1 divides I, and 0 is less than or equal to I is less than or equal to p minus 1 times p to the n minus 2. And in this case, this group is cyclic. So the only thing compatible with our formulas here and their explicit information is that the even groups are non-zero exactly in these specific finite number of degrees, no more, no less. And in fact, those even groups that don't vanish are all cyclic. So that's one thing. And then another thing to maybe observe is that so here's a sort of other remark that kind of tells you what sort of information is in the picture. And if I look at the TC of, just to throw an example out there, z mod z to the 7th, what do we know about this? We know it mod 7 v1 to the 5th is known. And the degree of v1 to the 5th is something like 201,682. Okay, something large. So that implies that we know pi star of tz of z mod z to the 7th mod p for star less than or equal to something like 201,600. Approximately something like that. So we know the mod p groups in quite a large range, especially as this number is growing. And then because of this complete understanding of the even homotopy groups, modulo their orders, that tells us the number of summands in pi star of Tc of z mod 7 to the 7th for star less than or equal to this 201,600-ish number. Right, so we actually know not just the orders, which is what comes out of Antu, Krause, and Nicholas, but in a range that increases here, we know the number of summands in the group as well. I think it is probably possible to just compute these things. So there's some hope that the V1 Bachstein can be computed completely, but that remains to be seen. Okay. And so maybe I have, what, 5 more minutes or something? So let me just give one additional application. Let X denote a p-torsion-free F-smooth, which is some technical niceness condition, QCQS p-adic formal scheme of dimension d. So by that I mean the Kroll dimension of the special fibers. And so we could set b of d to be some quantity like the ceiling of the log base p of the ceiling of d plus 1 over p minus 1 plus 1 ceiling plus 2. Okay, so some number depending on the dimension and the prime. Then the mod p etale cohomology groups hi at x eta mu p tensor j may be recovered solely from knowledge of x p to the b of d equals 0. So this is the cohomology of the generic fiber. This is the cohomology when you invert p on this p torsion-free formal scheme. And I claim that you can actually completely understand the mod p cohomology of the generic fiber from some reduction that depends only on the dimension. So some prototype of this kind of result can be found in things like Fontaine-Messing, but this gives you a sort of very general expression. And the reason something like this works is because by work of, say, Bott and Matthew, if I look at the mod p syntomic cohomology of x, that has an explicit bound on its V1 torsion. So it can have V1 torsion, but it can't have high power V1 torsion. So if you want to understand what happens when you invert V1, it suffices to understand what happens when you mod out by some power of V1 that exceeds Bott and Matthew's torsion bound. And then maybe I will just finish by saying that we can even do a little better. So we have a few results in the paper on the archive that do a bit better. So for example, if x is affine, the etale cohomology, the mod p etale cohomology of the generic fiber may be extracted from xp cubed equals 0. So regardless of the dimension, as long as you're affine, you can learn the etale cohomology of the generic fiber just from the mod p cubed reduction. Again, this follows from the fact that we're in some kind of smooth situation where we have some control over the power of V1 torsions that appear. All right, thank you.
Other questions, comments? Louder.
Do you have version for the factorization of p-adic result for higher height?
So I think, again, that part where we're not working at the level of syntomic cohomology, but at THH is something we're actively writing down. And I think I don't see any issues with writing it down at higher heights, so I expect a similar argument would go through, but we haven't worked out all the details.
Other questions, comments?
What are the applications of that higher height stuff going to be to?
Well, I mean, maybe haven't thought too much about that, but for example, you know, you could compute, you know, I guess you would learn things about varieties that could be lifted to over L or over the sphere. And I mean, the most naive thing to say is that you would be able to calculate things like TC of KU mod some power of the Bott element or something like that.
So TC of height 1 things.
You know, so this kind of thing is about TC of Z mod P to the N, which is like taking height 0 but quotienting out that, and so you take KU and quotient out V1 or something.